Okay, everyone. So let's talk about differentiation. So this is your x-axis, y-axis, and we have some function fx. So when I say differentiation, what you actually mean is to find out the slope at a point. Okay, so let us say we have a function fx and we have to find out the slope of this function at some point, and let us say that point is x. Okay, now to find out the slope at a point, what we are going to do is we are going to take another point, and the distance between this point and this point is going to be x, so this point is going to be x plus h. So the value of function at this point is going to be x plus h, and at this point it's going to be fx. And if you want to find out the slope that is passing, the line that is passing between these 2 points, if you want to find out the slope of this line, this is going to be rise over run. So if you see, this rise is going to be fx plus h minus fx. Okay, and run is going to be this length, that is x plus h minus x, that comes out to be h. So if you want to find out the slope of a line, okay, that is passing from fx and fx plus h, so that is nothing but minus fx divided by h. But since we are interested in finding out the slope about a point, so what we are going to do is, if you go on reducing this h, what is going to happen? Let us say at this point it is 1. If you go on reducing it 1, then 0.1, then 0.001, then 0.00001, and so on. If you go on reducing, what you are going to do here is you are going to apply limits. So if you do this, you are going to get the slope of a curve at a point, that is at this point, where h tends to 0, and this is known as your derivative. So what is derivative? Derivative is the slope of a curve at a point. So I think in your high school you might have studied about derivatives, and you might have used formulas for finding out the derivatives. Okay, like when you say derivative of x raised to n is nothing but what? Okay, yeah, so this is also one way, that is known as Leibniz notation for writing down the derivative. So if you want to find out the derivative of this, is going to be, and so on. So there are a lot of formulas that you might have studied in your high school to find out the derivative. But in real life, if you see, you are going to find out the derivative of complicated functions. Okay, so the problem is, if you want to find out the derivative of those complicated functions, your derivative is also going to be complicated. Okay, so that is why we talk about numerical differentiation. Okay, so in this chapter what we are going to do is we are going to discuss about finding out the derivative numerically. Okay, and the approach that we are going to use is known as finite difference approach. So when you say finite and difference, that means you are going to subtract something finitely. Finite difference approach. Okay, so what we are going to do is we are going to derive the formulas for first derivative, second derivative, and so on. So once you understand how to find out the derivative, first order approximation here, or first order finite difference scheme for the first derivative, you can extend it for finding out the formulas for other derivatives. Okay, so let us say, okay, before doing that, let us talk about Taylor series, because Taylor series is what we are going to do use for finding out the approximation. So let us say this is your function, this is your variable and this is your step size. Okay, so if you want to find out the Taylor series approximation of this function, it is going to be fx minus plus minus f dash of x h square divided by 2 factorial f double dash of x plus minus triple derivative and so on. So this is known as what? Your Taylor series. Okay. Now let us say we have a function, okay, y is equal to fx, okay, and let us say we have a point xi and we have 3 points, okay, and the step size here is h, so this is going to be xi plus 1, which is nothing but x plus h, and this is x, and this is going to be xi minus 1, this is going to be x minus h. Okay, so now this is going to be your yi minus 1, oh no, sorry, plus 1. This is going to be your yi, this is going to be your yi minus 1. Okay, so when you talk about yi, so your yi is nothing but what? Y of xi, and that is nothing but y of x, that is nothing but f of x. And when you say yi plus 1, that is nothing but y of xi plus h, and that is nothing but f of xi plus h. Okay, now if you apply your Taylor series approximation to this, you'll find out. Okay, now understand one more thing. I'll not be writing like this now. Okay, I'll be writing like this. I hope now you guys have understood. When I say yi is nothing but, what you have to do is you have to take y and substitute xi, and that is nothing but fx. Y is nothing but fx, so that means you have to substitute xi in fx. And I'm not going to write this down again and again, so I'll just be using xi in yi and yi plus 1 and yi minus 1, those kind of things. So let us apply Taylor series approximation for yi plus 1. So if you apply Taylor series approximation for yi plus 1, which is nothing but this, and when you apply Taylor series approximation, this comes out to be, if you see there, this is going to be y xi plus this is going to be h square divided by 2 factorial, this is going to be y dash xi, this is going to be h cube upon 3 factorial y double xi. Okay, so I told you that I'll not be writing down like this, but still, since this is the first Taylor series approximation, first time I'm using, so I'll write it down like this, but from next time onwards I'll not be writing down like this. Okay, so we know what is this. So if we rewrite this, this is nothing but yi, okay, and this is going to be h yi dash, this is going to be h square divided by 2 factorial yi double dash, sorry, this is going to be positive 3 factorial yi triple dash and so on. So this is going to be yi plus 1. Okay, let us say that this is your equation number A. Let us write down the same Taylor series expansion. Now this time I'm not going to write it down like this. I hope now you guys understand. So if you just use this formula and apply it here, so you'll find out this is yi minus h yi dash plus h square yi double dash minus h cube yi triple dash and so on. So let us say that this is my equation number B. Okay. Now let us take equation number A, and if you focus on equation A, okay, that is this equation. Now if you bring yi on this side, okay, and just keep this on right hand side and bring everything, that is yi and this everything on the left hand side. So this comes out to be yi plus 1 minus yi minus h square upon 2 factorial yi double dash plus h cube upon 3 factorial. I'm sorry, it's going to be negative since you are bringing it on the left side. Okay, and so on, and this is going to be y upon factorial, and this is going to be h yi dash. Now if you divide both in sides, okay, one more thing I missed here is that this series is going to continue. Okay, it's always important, this is important, that this is a series, so it will continue h into yi dash. Now we are going to divide h by both the sides, on both the sides, so this comes out to be yi plus 1 yi divided by h minus h upon 2 factorial minus h square upon 3 factorial and so on. Okay, now if you truncate your Taylor series at this point till here, okay, if you truncate your Taylor series here, so this additional term becomes your truncation error. So obviously you are truncating the series at a point, you're not taking all the elements or terms, not taking all the terms. So obviously there will be error because of this, and that error is known as truncation error. And if you see, the order of that error is going to be h. Okay, because if you see, h square and h cube is not going to make much of difference because h is going to be a smaller value, and when you square a smaller value it becomes smaller, so it's going to be of order h. So this truncation error is of order h. And if you see, the formula of y dash is yi plus 1 minus y upon h order h. So this is the formula, okay, for finite difference approximation. Okay, and this has a special name. This approximation is known as forward, so it should be forward finite difference scheme. So this is known as forward finite difference approximation or scheme. So if you play with your equation B, similarly you'll find out that you get another formula for the derivative, and that formula is yi dash, this is going to be yi minus 1 minus yi divided by h. So this is the formula of backward finite difference approximation. So this is your forward and this is your backward. Okay, so if you can see here, when you are going to use xi plus 1 and xi, it's going to be forward since you are using the function which is forward of xi. Okay, and when you use xi minus 1 and xi, this becomes backward. So when you talk about these 3 points, this is xi plus 1, xi minus 1. When you use this is forward, and when you use this 2, it becomes backward. Similarly, if you use this and this, that becomes your central difference scheme. Okay, so again, when you play with your equation A and equation B, okay, so when you subtract equation A from when you subtract equation B from equation A, okay, this is minus, you'll find out you are getting another equation of derivative, first derivative, that is yi plus 1 yi minus 1 divided by 2h, and the order here is going to be h square. So this is known as your central difference scheme. Okay, central difference, finite difference approximation. So this is a centered or centered, TERED, centered difference scheme. So when you use this point and this point, it is centered. When you use this point and this point forward, this point and this point is going to be backward. Okay, so this was for the first derivative. So if you play with your equation B, similarly, you'll find out that you get another formula for the derivative, and that formula is yi dash, this is going to be yi minus 1 minus yi divided by h. So this is the formula of backward finite difference approximation. So this is your forward and this is your backward. Okay, so if you can see here, when you are going to use xi plus 1 and xi, it's going to be forward since you are using the function which is forward of xi. Okay, and when you use xi minus 1 and xi, this becomes backward. So when you talk about these 3 points, this is xi plus 1, xi minus 1. When you use this is forward, and when you use this 2, it becomes backward. Similarly, if you use this and this, that becomes your central difference scheme. Okay, so again, when you play with your equation A and equation B, okay, so when you subtract equation A from when you subtract equation B from equation A, okay, this is minus, you'll find out you are getting another equation of derivative, first derivative, that is yi plus 1 yi minus 1 divided by 2h, and the order here is going to be h square. So this is known as your central difference scheme. Okay, central difference, finite difference approximation. So this is a centered or centered, TERED, centered difference scheme. So when you use this point and this point, it is centered. When you use this point and this point forward, this point and this point is going to be backward. Okay. So this was for the first derivative. Again, if you play with a and b, you will get another equation. Okay, and that equation is going to be for your second derivative. So if you add equation A with equation B, you will get an equation for second derivative, that is minus 1 yi plus 1 divided by h square, and the truncation error here is going to be of order h square. So this, when it is h, it's less accurate. When it is h square, it is more accurate. When it is h cube, more accurate. H raised to 4, obviously more accurate. So as the power of h increases in this order, truncation error, the error reduces. Okay. So this is for second derivative, and this is known as centered difference scheme. So if you see, you're using the point ahead and the point behind, so it has to be centered. Okay. So this is how you can derive formulas by playing, just by playing with equation A and equation B. Okay. So again, we'll just write down the table. So we'll write down the formula for first derivative and what is the error. So when you talk about y dash first derivative, this is the formula. Okay, and the error here is OH. So this is what your forward difference scheme. Then there is this formula. This is known as backward scheme. Then there is this formula. Understand that there is the denominator, this is 2h, and this is centered, but this time the order of magnitude of truncation is h square. That means this is more accurate than forward and backward. Similarly, there is another formula for the first derivative. But the good thing is this has an order of magnitude. The order of truncation error is h raised to 4. So obviously this is going to be very much accurate as compared to this. This is also a centered scheme. Centered scheme with fourth order approximation. Okay. Similarly for second derivative, this is going to be h square. And what is the error? Obviously it's going to be h square. Okay. And if you want a more accurate scheme for second derivative, it's going to be divided by 12x square. And what is the order? This is 2, 4. Okay. So this is also centered scheme. This is also centered scheme. If you say centered schemes are more accurate. Okay. So once we have discussed this, let us solve one problem.